Okay, so I have a video that I would like to do for the module 6 for sales statistics. So I have this started already. And I'm going to have to go pretty quickly because my first class starts in about 22 minutes and my original video was supposed to take 40. So I'm going to go a little quickly. So there's some notation that comes from this module that they expect you to know. So I wrote it down. Some of these are very obvious, like square root is very obvious. That's old school, but the sum comes from this letter right here. This is the Greek letter epsilon. Actually, it's capital epsilon, but you get my point. So it means to sum, to add everything together. So the sum of x squared is on the one variable stats on your calculator. When you go to stat, edit, you enter in all your data. Once you have your data, you go back to stat, scroll to the right so you get to the calculate, and we do one variable statistics. Make sure to calculate, and you will see it right here. It's the third one down. The second one down is just a plain sum of all of your numbers. So the calculator will do those for you. A capital P with a parentheses of X, this means probability of event X happening. And that X will be defined in your question with the context. So mu, this is the Greek letter mu, it's the probability, it's the population mean. Sigma is the sideways 9, it's a population standard deviation. Lowercase p is the probability of success. Lowercase q is the probability of failure, but it's also equal to 1 minus p. 1 minus the probability of success is the probability of failure. So capital S, lowercase p next to it, this is the standard deviation of a probability. X bar p is the mean of a probability sample. I guess I should have said this one's for a sample. Okay, X is the number of successes, however many that is. N is the number of trials or data values. How many numbers do you have? Capital P of S, this is the binomial probability of success. You'll know what a binomial probability is later, but for now, it's the binomial probability of success. P of F is the binomial probability of failure. So these are just notations. Now, if you are checking a probability distribution to see if it is actually a probability distribution, you should be able to add all the probabilities together and it equals 1. If it does not equal 1, then it is not a probability distribution. Okay, because remember, probabilities, it's the number of successes divided by the total number of possible outcomes. So if I have the total number of possible outcomes divided by the total number of possible outcomes, I get 1, which is what I should have at the very end if it's a binomial distribution, if it covers every single possibility of a specific situation. Okay, in a probability, we have something called an expected value. Okay, the expected value is extremely important. And what you do is you multiply, okay, the value of your success by the probability of that success. And then you add it to the product of the next number of successes by the probability of success. So by hand, this expected value, we call it capital E of X, is 0 times 0.157, right? That's my first line, plus 1 times 0.402 plus 2 times 0.343 plus 3 times 0.098. Okay, and then I plug all of this into a calculator, and it should tell me the expected value. 0.157 plus 1 times 0.42 plus 2 times 0.343 plus 3 times 0.098. All right, so my expected value for this situation is 1.382. Okay, it's for probabilities, this is sort of like a mean. This is like an average, okay? The expected value okay, is if I randomly had a situation happen, my expectation is that I would approximately have 1.382. Okay, so somewhere between 1 and 2 is what's going to happen. Okay, by the calculator, you can do this using the lists. Okay, so stat edit gets me to the lists. I'm going to use list 1 for the x's. So 0, 1, 2, 3. I'm going to use list 2 for its corresponding probabilities. So 0 is in my first row. That means the first row of list 2 needs to be its corresponding probability. Okay, so on and so forth. Okay. So you can do operations using these lists. Okay, so once I've entered in all my data to the lists, I'm going to quit out of this and go back to the home screen. So right here above stats is the lists in blue. So if I press second list, it'll give me the list of the names, and I can do any operation I want with these lists. So I'm going to take list 1 and I'm going to multiply it by list 2. And then I'm going to store that. Storage is right here. I'm going to store that in list 3. So second list 3. So I can see what's going to come. Okay. So you can see the list of the numbers that are the multiplication. So I could go back to stat, edit, and I can look. And there you go. There is the multiplication. So now if I go take the one variable statistics, but I take it from list 3, not list 1. So I need to go back to the blue list. So second stat, and list 3 was my multiply. I can do calculate, and right here, here's my expected value. Okay, now when you have as small as 4 data values, it may not make sense to use the lists way to do this, but if you had something like 17 possible situations, then maybe these lists to find the expected value makes more sense. 382. Okay, so this is everything from oh, almost. Okay. There was one other thing I wanted to talk about from 6.1. Okay, when you are plugging in a value, to the calculator, make sure it's in parentheses. Because if you don't, it's not going to do the right thing with it. Okay, so an example is I have mu plus 3 sigma, and then I'm going to tell you mu is 2.68, and I'm going to tell you sigma is 0.62. Okay, so I've given you the data values that you needed to answer this question. You have to plug them in appropriately. So 2.68, I know I have this value, and 0.68, I know I have that one. And they can both go right into the equation. So mu is 2.68. Notice I'm using a parentheses when I'm plugging it in. Plus 3 was a part of the equation, and sigma is right here of 0.62. And because I'm plugging something in, I use parentheses. So I can grab my handy dandy calculator. 2.68 plus 3 parentheses 0.62. Okay, so my answer for this one is 4.54. Okay, if you do not put it in parentheses, it may not do this correctly. So please make sure to do so. That's very important. So now while I get set up for 6.2, if you're only needing 6.1, you can go ahead and leave the video while I get ready for 6.2. Okay, so we have discrete and continuous random variables because this one is all about random variables just in general. So when I have discrete and continuous, I have to be able to tell which one is which. So the word discrete means separate. Okay, it means that they are truly separated. So discrete random variables are random variables with countable data. What I mean by that is something that is literally counted 0, 1, 2, 3, 4, 5. They are numbers that are truly staccato, truly separated. So some examples of a discrete random variables would be number of people. Number of people. You can't have half a person, y'all. You have to count whole numbers. 1, 2, 3, 4, 5. You cannot separate that. Okay, another one you can have is some other countable number. So in a deck of cards, the number of hearts, right? The heart suit, there should be 13 of them. So this is what I mean by a countable data. This is something that when you're gathering this data, it's something you are truly counting. Continuous this is with measured data, truly measured. Okay, because it's with measured data, these will be intervals. Okay, so what I mean is like between 1 and 5, anything between 1 and 5, which can be 2, 3, 4, or it can be 2.17568, anything between. So anything between 2 and 4. Okay, so literally anything. So 2 less than x less than 4. This is the example of the interval notation of this particular question. So this is the huge difference between discrete and continuous. Now, most of our probabilities are going to be a discrete situation, but you need to recognize the difference between the two, because if you do not recognize this sort of thing, then you're going to get in trouble. Okay, you're going to get in trouble because you're going to use the wrong form of probabilities. Okay, so we have things called probability distributions. Okay, probability distributions, these are histograms that should be bell-shaped. So I can draw a little mini example. Okay, so as you can see, there's a bit of a bell shape coming from this data. Okay, this is what it should be. And I don't mean exactly bell-shaped, I'm saying approximately bell-shaped. Now, there is a way to do this on your calculator. I'm not going to use the time to do it here because I'm running out of time before I get students. So I'm going to say, watch the third video in 6.2 for calculator help for these probability distributions. Okay, so this is what you're going to want to do to get that one. All right, they should be bell-shaped. Remember that, bell-shaped. That is the key. So I'm going to hop over to 6.3. So again, if you don't need 6.3 right now, you can pause or stop the video. All right, so 6.3 is for binomial probability distributions. Now, the word binomial means two terms, okay? In our case, this means two outcomes. You can have a success or a failure, and this is all you can have. Now, that success will be defined by context. Like your success could be that you rolled a 3 on a 6-sided dice. Your success could be that it rained that day. Like there's all kinds of possibilities for what a success could be. And it's totally up to the situation to define that. But to use a binomial probability distribution, you have to have 4 requirements. And these must be met. If these are not met every single time, then you cannot use the probability distribution math and it will be harder. Okay, so the first thing is you need a fixed number of trials. Okay, so they have to tell you, I've only done this 50 times every time, or 20 times every time, or 7 times every time. But they need to tell you exactly how many, and they need to say that this happened every time. The second thing is that your events must be independent. If you forgot what independent means, that means that the event of one outcome will not affect the event of the next one. Okay. The gender of a baby, or not gender, the sex of a baby is decided independently. Okay. If your first child is a girl, then it's not going to affect the gender or the sex of your second child. They're either a girl or a boy, but it's still 50-50 shot. It doesn't change just because your first one was a girl. Okay. If you roll a dice, okay, you roll a dice and you get a 2 the first time. Rolling the dice the second time, you are not any more or less likely to get any of the other values. That 2 will not affect what comes next. So that way it makes this, that's what makes them independent. Now, the key for independence, okay, is that you need with replacement. Okay, if you're drawing things from like a hat, you have to replace it to maintain independence. Okay. At this point, hopefully you guys know what that means because the last unit really required that. So the third thing is that you must have only 2 possible outcomes. Okay, and these are defined as a success and a failure. Now, this does not necessarily mean that you're flipping a coin and you've got heads or tails and your success is that you get tails. You can still do this with like a 6-sided dice. If you have a 6-sided dice and your success is that you roll a 2, then that means that your failure is you roll anything but a 2. You roll a 1 or a 3 or a 4 or 5 or 6. Like this is the difference about success and failure is that it doesn't have to be like a 50-50 shot. Okay, you can have a much less probability of success or much higher probability of success than the failures, but it's completely situationally based. You just need to be able to make sure that there's only one version of success and then one version of failure. But the failure could just be not successful. If there's nice, obvious differences between the situations, like rolling a dice or flipping a coin or pulling a card from a deck or things like that, where there's an obvious difference between each of the situations that's happening, then your failure could just be that you were not successful. Okay, so number 4, the very last requirement is that your probability of success must remain the same for every trial. Okay, when you're rolling a dice, I just keep using this one because you guys have all rolled dice in your life. If you roll a dice, the probability of getting a 2 is 1/6, right? There's 1 2 on a 6-sided dice. So the probability of getting a 2 is 1/6. And it will always be 1/6. Your dice is not going to randomly grow another side that's a 2 also. That's not going to happen. It's always going to be 1/6 no matter what. Okay. So, oh my goodness, I had to sneeze. Okay. So let me say example. probability of rolling a 2 on a 6-sided dice. Okay, it will never change. Every single time it's 1/6 over and over and over again. Okay, so I'm still on 6-3, but I ran out of room. So still on 6-3. All right, so they have a capital P, capital S to tell you that this is the probability of success. This is just their notation. And they use a lowercase p as its variable. Okay, the probability of failure. This is its notation. And it's defined as Q, which is 1 minus P. Okay. So success and failure. I think I've defined everything else as before. Just another mark. Make sure if it's without replacement, then it is not binomial. That's a pretty obvious thing to see because I'll have to say without replacement in the question. So it's a pretty obvious this doesn't work. Okay, so standard deviation and mean. Okay, so for a probability distribution, the standard deviation of a probability is the square root of the number of the number of possibilities times the probability of success times the probability of failure. Okay, the mean of a probability is the number of possible outcomes times the probability of success. Okay. So I can give you an example. I'm still going to use the 6-sided dice. So I'm going to say a success is rolling a 6 on a 6-sided dice. Okay, well, it's a 6-sided dice, so the number of possible outcomes is 6. And the probability of success is there's only 1 6 on a 6-sided dice. So 1/6 is my probability of success. Okay, that means my probability of failure is getting a 1, 2, 3, 4, or 5. So that's 5 out of 6. I could have also done 1 minus 1/6, then it would have given me the answer. So the standard deviation is the square root of 6 times 1/6 times 5/6. Okay, so I'm going to use my handy dandy calculator for this. Okay, so because I'm plugging in numbers into an equation, I'm going to put those numbers in parentheses. And I'm going to say enter. Okay, so the standard deviation for this situation is 0.9129. Okay, most probabilities, they want 4 decimal places. My teal is running out, so I'm going to switch to purple. Okay, and then the mean was the number of possibilities times the probability of success. Okay, so again, if I'm going to plug this into a calculator, 6 times 1/6 is 1. Okay, so the mean for this situation is 1. All right, here's how I find the standard deviation in the mean. I don't recommend plugging in all of these data values into a list and trying to figure it out that way, mostly because that's kind of worthless. This is just as easy to do. Just use the formula. Remember, this formula is on your formula sheet that I gave you at the beginning of the school year. Use that formula sheet. Get comfortable with what's on it because you're going to need it for these next few modules. So write it down. Keep it. I only have 7 minutes. So I'm going to stop this video at 6.3 and I'm going to make a new video on 6.4 and it'll come right after. I'll start it right from here and go on, but I'm going to have to make it at the end of the school day. So I'm going to stop recording. and I'm gonna post this so y'all could at least get started.